Okay, good afternoon, everyone. So 今天我们讲到 free body diagram 还有 forces in equilibrium 嘛，老师有教到吗？这个两个，还是他就这样子加进去吧？你的 exam 有没有好像大概讲到这个两个，尤其是那个 forces in equilibrium，因为那个是蛮多的 equilibrium forces，所以我不知道全部会 involve 啦，还是只是单单一些 section 罢了。Not sure. Okay, no. Okay, okay. I think based on the message, like the info you send me, I think the finding resultant force definitely is going to come out. Finding resultant force, like the vector diagram. Okay, we'll go through that one in this lesson. How to find resultant forces in different systems, and for the equilibrium of forces, that one I'm not sure whether your teacher is going to include that one, but I will still teach you a little bit about the equilibrium of forces just in case if it comes out lah. Okay, so okay, without further delay, let's start. Let me get my pen. Okay, so let's start with the free body diagram, FBD. Now, what is a free body diagram? Let's say a scenario. Let's say suppose that we have an object resting on a surface. Identify all the forces acting on this system. So this system, we have two bodies. One is the ball, one is the surface. So first is that because the ball is resting on the surface, so there's a force applied by the ball on the surface. F by object on surface. And then according to Newton's third law, when you apply one force and then that object will apply the same force opposite direction, right? So the surface will also push the ball in equal magnitude of forces. So there's another force acting on body number one, F by surface on object. Two forces, and these two forces having equal magnitude, right? Now, is there any other force? There's one mg, right? Mg actually acting on two objects because you got two objects here. So we got one mg for the surface, we got another mg for the ball. But here I'm going to label only the mg acting on the ball. Okay, so we have another force here, F by, who is applying the mg? The earth, right? By earth on object. Now, total we have three forces. If I want to draw the free body diagram, let's say I want to draw free body diagram of the ball, then I will make the ball free from the system. This is the system of two objects. I make the ball free, so I only draw the ball. You can assume that the object is like a point, or you want to draw the object also can. And then we only label the forces acting on it. Now, be careful. What force do we label here? We got three forces, right? F by surface on the object. So this is included on the object, right? This one also force by earth on the object, yes, but this one not included because this is the force by object on the surface. This is if you want to draw the free body diagram of the surface, then only you take this force. Okay, so since we are drawing free body diagram of the ball, so this one I will discard and I only include these two forces. So I draw it here, F. This is, we call the reaction, right? Because it is resting on a surface. So the surface presses it back. This is, we call the reaction force. And then we have another one downward, mg. Now, when you draw the free body diagram, a few things you need to be careful. The length of the force should be, the length actually represent the magnitude. Magnitude equals to the length. Okay, so if these two forces, they are equal, then they should have the same length. Okay, they should have the same length. So I want to draw same length here, and just to represent that these two forces are equal. Okay, and also the direction, you cannot change it. You can draw it like this, or you can draw it on a point, like assuming the object is 1 point, we have R, and then we have mg like this. Okay, so drawing free body diagram, very, very important. You have to learn how to draw it, label all the forces. The reason we draw free body diagram is to show all possible forces acting on one single object, only one single object. Okay, FBD is for one object only. If you want to draw the FBD for another object, then you have another diagram. Okay, so at one time, we only analyze one object. Now, why do we want to draw free body diagram? The main purpose of drawing the FBD is to find out whether forces are balanced or unbalanced. Okay, that's the end goal. We just want to know whether the system is balanced or unbalanced. Balanced as in what? As in the forces, balance. In a balanced forces, what happens to the resultant force? Net force. Net force in a balanced system is 0. Okay, now, for example, here I have an object. There can be many, many forces acting on this object and still be balanced. Here, 5 Newton. Here, 5 Newton. Here, 8 Newton. Here, 8 Newton. Another 2 more here. 10, 10. How many forces acting on the object? 1, 2, 3, 4, 5, 6. 6 forces acting on it. But in this case, is it balanced or not balanced? It is balanced forces. How do we know? Balanced forces means that they cancel out each other in each direction. Okay, this force coming here cancel out by this force. This one cancel out by this one. This one, 10 Newton, cancel out by another 10 Newton. So leaving no more forces, there's no net effect of forces. So it is a balanced system. Okay, you cannot know whether you cannot know whether an object is balanced or not without drawing the free body diagram. So first, you have to always draw the free body diagram to analyze. Okay, after we draw it, we analyze the forces, and then we see, okay, it is balanced or is it not balanced. Okay, so why do we want to know whether it's balanced or not? Because if it's balanced, means what? Two scenarios, if you still remember it at our very first earlier chapters, right? If it's balanced, you got two scenarios. First is it is at rest. Second, it is moving. If it's initially moving, then it will be moving at constant velocity. In these two cases, forces are balanced. Okay, so the forces acting on the ball is balanced. The weight is balanced by the reaction. So in this case, is it moving or rest? This one is at rest. Okay, at rest. So how does it look if it's moving? If it's moving, maybe it's moving like down at a constant velocity. That one can be balanced also. Okay, so back to this one. In a balanced system, the algebraic sum of all forces, this one, algebraic sum of forces. What does it mean by algebraic sum? Algebraic means I give it a sign, plus minus. Sum, I total up. All the forces will be equals to 0. This one, 5 Newton in this direction. The one that going against it, I will give it a negative sign. 10 Newton going in this direction. The one that going against it, I will give it a negative sign. 8 Newton, the one going opposite, I will give it a negative sign. I take the sum of forces, summation of all forces, 8 plus negative 8 plus 10 plus negative 10 plus 5 plus negative 5. You get a 0. That is the meaning. of algebraic sum. Okay, sometimes you will see this word. Algebraic sum of forces is 0 when the system is balanced. Okay, when the system is balanced. And in a balanced system, two things are either it is at rest or it is moving at constant v. There is no resultant force, no net force here. Okay, so we can only determine this when we draw the free body diagram. Now, another case would be an unbalanced scenario, unbalanced system. Okay, so imagine if I remove the surface, this one, I removed it. And now if I remove the surface, right, then the force by the surface gone already, disappeared. This one disappeared. Force by surface, which one? Okay, only this one. There's no more force by surface. So the only force left is the yellow color force, right? The downward mg. This is the ball and it's acting by F by Earth on the object. And since it is moving downward, so you have another force that is air resistance. Okay, air resistance. So air resistance is going upward, but this air resistance is, we're going to assume that air resistance is smaller than the weight. It cannot be larger, right? Because larger it would be moving up. So it is smaller than the weight, or it could be equal as well. Okay, they're possible. That's possible also. So let's assume that the air resistance is smaller than the weight. So the ball is accelerating downward. Okay, air resistance, we call it drag. I'll label it D. Okay, drag. So in your free body diagram, then you draw like this. This one, okay, mg has a certain length here, and then the drag would be smaller, shorter. Okay, D here. This is to show that there is a net force acting downward. Is this a balanced or an unbalanced system? This is a unbalanced system. Okay, if this is 5 Newton, here, this is, let's say, is 10 Newton. Take the algebraic sum of forces. Okay, sum of forces equals to this one, take it positive. So the one going against it is negative. So 10, negative 5. 5 Newton, this is downward. Okay, so what force is this? This is, we call the net force or the resultant force. So resultant force causes what? Resultant force causes acceleration, not motion. There's a difference. Resultant force does not cause motion because one object can be moving without resultant force. Okay, that is like moving with constant v. Resultant force causes acceleration, not motion. Okay, now let's look at some other types of system where you are asked to draw the free body diagram. Okay, another one. Let's say you have a object hanging by 2 strings, like this, 5 kg. Okay, if the question asks you draw the free body diagram, then we identify all forces. Now, first, you need to know what are the all types of forces out there. Okay, first you have applied force. Applied means the push and pull. It can be applied by a person or another object. That's what we call applied force. Okay, and then we have gravitational force. We have frictional force. We have tension. Tension is forces in strings. Okay, in strings or spring. Okay, what else? We have air resistance, right? Drag. What else? We have normal reaction. Okay, normal. It's a reaction force. Reaction force. All these forces, the easiest way to remember, okay, we put it in short. We put it like this. You remember this. F equals to MA, mg, FTR. Remember this. Okay. whenever you want to label free body diagram, okay, think MAMG FTR. MAMG FTR. MA is the applied force. MG is gravitational. Small f, friction. T, tension. And the last one, reaction force. Yeah. Now, how do we label the free body diagram for this system here? Okay, I'm going to make this object free from the system, right? What object? The 5 kg mass. I'm going to treat it as a point. So I write a dot here. Okay, like a point mass. And then I label, okay, what are the type of forces? I got mg downward. 2 strings, right? So I got tension on each string. So I got 2 tensions. Okay, how do we label the tension, by the way? If you look at, like, let's say like you have a string hanging an object. How do I label the tension in the free body diagram? Imagine the last molecule, the last molecule in the string that is attached to the object here. The object is trying to pull the molecule down. And then the second last molecule, the one beside it, slightly above here, right? The last molecule is pulled by the object downward, so it's being stretched away from the second molecule. Okay, you got 2 molecules like this, 2 molecules. The last one is being pulled downward and is being stretched away from the second molecule. So think about the string is like elastic, right? Whenever you try to stretch it, it comes back. It tries to resist you, right? It tries to resist you. So that resistance has a force. We call it the tension. The tension. It is developed inside the string or the spring. Okay, it is developed. The moment you stretch it, the force is developed inside the spring. Okay, so imagine you pull the last molecule down, right? And then the molecule tries to come back. So there is a force upward. There's a force upward. And we label, the way we label the tension is out of the object. Okay, now out of the object, this is the object and the arrow is pointing away from it, going out. Okay, imagine it is going out from the object. This is the way we label tension. Not like this, okay, not downward. Okay, so going up, because the force is going up, is pulling the molecule back. Okay, so this is T. If you have another object on the other side like this, how do we label the tension? Okay, let's say we make it flat like this. 2 objects placed side by side, separated by a string. Imagine like you stretch them. Label tension is we label out of the object. On this side, the right hand side, also out of the object. Tension, tension. Okay, so you got 2 strings here, right? One tension going out to the left, and another one go out to the right here. Tension 1, tension 2. So there goes your 3 forces. Is there any other forces? Air resistance, no air resistance. Friction, there's no friction. Okay, that's all. Reaction, no reaction because there's no surface. Okay, whenever you have a surface, then there's always a reaction. So no surface, no reaction. So my free body diagram would look like this. 1 point, and then mg, T2, and T1, like this. That is my answer, FBD. Free body diagram of what? Of the mass. Only one single object. If this given the angle here, let's say 120, then you label in the diagram 120. 120. Okay. Okay, how about this one? Draw the free body diagram of a box resting on like a sloping surface. Okay, draw free body diagram. Identify the forces MA, MG, FTR. Is there any MA force pushing it? We are going to assume this is at rest. Huh? It is resting. It's not sliding down, right? It's not sliding down means that the surface is rough. There's a friction. There's friction. Okay, MA don't have. MG, wait, yes. Okay, label downward MG. F, friction. Yes, there's friction. Label, how do we label it? Imagine that this box is about to slide down. Okay, it's about to slide, but it's not sliding because of the friction. So the friction will be opposite to the motion, going up. Okay, going up here. And this friction, the way I label it is parallel to the ground. The ground is sloping like this, right? So the friction is also parallel to it. And then T, tension, don't have, so skip it. Reaction, is there any reaction? Yes, because it is resting on a surface. But this surface is sloping. Okay, in a flat surface, your reaction is vertical. Flat surface, your reaction is vertical because it has to be 90 degrees to the surface. In a sloping surface, like slanted, your reaction is also slanted like this because reaction is always 90 degrees to the surface. Okay, so because the friction is parallel to the surface, reaction is perpendicular to the surface. So the reaction and the friction is 90 degrees to each other. 90. Okay, put it in free body diagram. Dot, I have mg down, and then I label reaction and friction. So friction in this direction, F, and reaction, R. And then I do a 90 degree here. This is my free body diagram for this object. Okay, so what is a free body diagram? It is a free body diagram is a diagram that shows all forces acting on one single object. Whether it is balanced or not, we have to analyze it. Analyze what? Analyze the free body diagram. Okay, so I write it down here. A free body diagram shows all forces acting on one single body. Whether it is balanced or not balanced, the net effect of forces needs to be analyzed using vector summation. Please write this down. Okay, a free body diagram shows all forces acting on one single body. Whether it is balanced or not balanced, we have to analyze the forces by finding whether there is a net effect of forces using a method called the vector summation. What is a vector summation method? Okay. In the next part, I'm going to talk about how do we find resultant forces, okay, given a free body diagram. Now, if you want to take a screenshot, you take it now. I want to erase this. Okay, now, suppose we have a free body diagram here. Force acting 40 Newton vertical and horizontal 30 Newton. Is this a free body diagram? Yes, right? Free body diagram, because there's only one object and it's showing the forces acting on it. Okay, now we want to analyze this free body diagram. We want to find out what is the resultant. Or it can be, if you want to know whether this object will stay at rest or moving or accelerate. How do we know? We analyze the forces. Okay, using a method we call the vector summation. What is it? Now, vector summation, you can think of it like a triangular rule. Okay, a triangle rule. There are two rules that we can use in vector summation. Triangular rule or parallelogram. Okay, now I'm going to talk about the triangular rule because that one is simply because it's easier to use. Okay, but any of this, it gives you the same result. Okay, now let's say I'm going to use the triangle rule. Vector summation means I'm adding up the vector. What is a vector? A vector is like this arrow here. This is a vector. It is showing you 40 Newton in this direction. That is one vector. This is another vector telling you that it is 30 Newton to the right. Okay, so the arrow is the vector. Force is also a vector. Okay, so I'm trying to add up the vector here because I want to see the result, the net. Okay, you can see that these two vector is in different direction, right? One is vertical, one is horizontal. So when adding the vectors, guys, when adding the vectors, I want to pick a point. Okay, just find some space where you can write, where you can draw. Okay, I'm going to pick any vector to start with. To start from the origin. Okay, this is the origin. I pick any vector. Okay, let's say I pick the 40. Now I pick the 40, I move it over here. Okay, draw it without changing the direction of it. 40 Newton going up, vertical like this. And then from here, I'm going to join to the next vector. 30 to the right. Okay, now the way I join, guys, the way I join, I have to join to the tail of another vector. How do I join it? Here. 30. Okay, the 30 should be shorter a bit, right? So let's say like this, 30 Newton here. This is how I join the vector. What I'm doing here, I'm adding up the vector. I'm doing vector addition. Okay, now the wrong way to join it is like this down here. No, because this one is the tail and the tail. It cannot, not tail to tail. It must be the head to the tail of another vector. Yeah, so I do it like this. Now, is there any other vectors? No, right? Only two vectors. So that's it. This is the starting point. This is the ending point. The resultant vector would be from the start to the end. Okay, from the, notice that I say from the start to the end, not the end to the start. So common mistakes, student always draw like this, going up, going to the right, and then come back like this. Not like this, okay, so we always goes from the start to the end. So we draw like this, and then we put double arrow just to say that this is resultant. Okay, so 40, 30, and here is 90 degree, right? Here is 90 degree, they are perpendicular. So here I have done a vector addition. So I can use this to find the resultant force. How do I find it? This is a right angle triangle. So you can use your Pythagoras. Okay, FR equals to square root 40 square plus 30 square. Okay, what do you get? 50 Newton. So your magnitude of the resultant force is 50 Newton. Now, do we end here? No, we don't stop here. We want to find what else? Because we are dealing with vector, right? So now we only get the magnitude, right? We only got the magnitude. We need to find the direction as well. Direction is in terms of angle. So we want to find an angle. Which angle we want to find? Okay, let's say I want to find here. This angle here. Okay, so we can simply use the Socha-Tua. Sine, okay, tangent theta equals opposite side 30 over adjacent 40. Angle equals to, okay, 30 divided by 40, tangent minus 1. 36.87 theta. This is my direction. After you find this, draw it in the diagram. Show where is your resultant force. Okay. Now, these two component of forces, 40 and 30, right? When we add up these two, we get this FR, resultant force. Okay, label it in the original diagram. How do we relate? You see the angle that you found. This is, what angle is this? This is the angle between the 40 Newton and the resultant force. Okay, meaning that it is 36.87 degree to the right. Where is it? Here, right? So this is the FR. You label the angle here, 36.87, and FR is 50 Newton. That is your answer. Okay, so this is the resultant force. Is this balanced? Now you know, okay, it is not balanced. So what happened then? This object will accelerate in this direction, even with an acceleration of how much? You can calculate. F equals to ma. Okay, put in the force, resultant. This is resultant, net force. So 50 equals to whatever the mass. Okay, take 5 kg. 5a. Acceleration is 10 meters per second square. Okay, if the question wants you to find what is the acceleration, okay, then you do FMA. It will be accelerating in this direction with a 10 meter per second square. Okay, right here, unbalanced system. Okay, let's try another one. Let's try another one. Oh, I still got 1 minute. I create a new link and we continue from there.